Hey everyone, this is the culmination of electricity and magnetism. A lot of different people were doing independent research and discoveries with electricity and magnetic fields, and we talked about Gauss, we've talked about Faraday, we've talked about Ampere. What Maxwell came along and did was combine all the equations that we've got from these scientists and put them into one unified equation. So let me go through each of the four Maxwell's equations and we'll explain what they actually mean in the end. So the setup that Maxwell envisioned for combining all of these equations was this. It's a battery and a capacitor. And we know what happens with a battery and a capacitor. The battery is going to push charge and create currents that go through the wire. And as they go through the wire, it's going to pile up positive charges on one plate and negative charges on the other plate. Once we have charges piling up, we know that charges will create electric fields, and those electric fields will be set up between the two parallel plates. Nothing new there. But we also know that since there is current moving in the wire, there are also magnetic field loops that's set up around the wires. So there's a magnetic field around the wires as the electric field is growing inside of the capacitor. So what Maxwell wanted to do was surround one of those capacitors with a Gaussian shape and look at the magnetic field that's set up around this surface area and how they related to the electric fields that were passing through this little Gaussian shape from one plate to the other. Is there a connection between magnetic fields and electric fields? Let's go through all of the equations. The first equation you looked at was Gauss's law. We know Gauss's law very well. It's the integral of E dot dA, which is Q enclosed over epsilon 0. It's the relationship between electric field and charge. If you have charge present, then there must be electric flux, and electric flux means that there is electric field, which means that we can have electric fields from a monopole. We can have one enclosed charge there and have an electric field if we surround it with a Gaussian surface. So that's equation 1. Equation 2 is Gauss's law for magnetism, which was very similar. Remember, we did B dot dA, and we surrounded magnets with Gaussian spheres, and we found out that any sphere we had and we surrounded a magnet gave us a B dot dA of 0, meaning we couldn't just isolate north and south pole. Every single time we did that, we got a dipole for magnetism. Atomically, what we'd have to say is we'd have to split the electron in half to actually get a monopole, a north or a south. The third equation here is Faradays EMF, the induced EMF we've been using this entire chapter, saying that if we have a change in magnetic flux over time, we're going to get a voltage set up. And another way to write that out is to say that voltages, remember, are electric fields times distances. So electric field times displacement, if we integrate that side, the electric field is equal to a changing magnetic flux. So electric fields get created by varying a magnetic field. And we saw that by surrounding changing magnetic fields and looking at these induced currents. Currents only come from a voltage. A voltage is energy given per charge. And if there's a voltage present, we said there must be an electric field present. The electric fields don't have any start and end point like they did with singular charges, but the electric fields are perpendicular to the magnetic fields. So if the magnetic field was into the page and changing, you can have an electric field that was perpendicular to that set up in a wire, push charges and make them move. So then that brings him to his fourth equation, and really his fourth equation is Ampere's law. In Ampere's law, we've talked about it being B dot dL. That was trying to find the magnetic field around Amperian loop. And remember that equals mu 0 times I. We called it the I that penetrates, or the I that is enclosed by that flat Amperian loop. But looking at that last equation, something was missing. Maxwell had to add a piece to this formula to talk about how the electric field changing creates a magnetic field. And he added in this little piece, mu 0 times epsilon 0 times the change in electric flux over time. The electric flux through that Gaussian sphere. He called that the displacement current. So what is that all meaning? So what is happening here? As current is flowing onto that plate, one plate is becoming positive, the other is becoming negative. We're having a change in the electric flux through this Gaussian sphere here. As more charges pile up, we're getting a larger increase in electric flux through that line. But since we have a current, remember we have a magnetic field around this loop. And the magnetic field is not constant because as more and more charges grow on the capacitor, it's actually going to start shutting down the circuit. We're going to get a change in the magnetic flux over time and that magnetic field strength as the electric field grows. So what does this all mean for us? Maxwell said that any changing magnetic field creates an electric field, and vice versa, a changing electric field will also create magnetic fields. So when we talked about the capacitor there, the magnetic field means there's current flowing onto the capacitor. And as the magnetic field is changing and decreasing, the electric field is increasing inside the capacitor. If you discharge that capacitor, that electric field changing creates the magnetic field in the currents in the wire. Well, what Maxwell said was that these alternating fields, these changing fields back and forth, create an electromagnetic wave. And they create a wave that travels at one particular speed. And when you solve for that speed, and when you do that, you get a value of 3 times 10 to the 8th meters per second, which is a very special speed that we've talked about many times in class before. This is the constant, the speed of light. So what Maxwell proved was that using all 4 of those equations, changing magnetic fields create electric fields, and they travel at the speed of light. So light is nothing more than an electromagnetic wave. So how do we create electromagnetic waves? Well, like you can see here, there's a radio station, and it says to move the electron. So if I move the electron up and down, you can see that an oscillating, moving back and forth electron is sending out an electric field up, then an electric field down, an electric field up, electric field down. Let's put it on oscillation mode. If I have this oscillate at a particular frequency, you can see that the electric fields are changing many times a second, and changing electric fields will also create changing magnetic fields. So what you get is a wave that has 2 components to it. It has a magnetic field and an electric field that as they change, they oscillate back and forth and create each other. Electric fields create magnetic fields and vice versa. So the only way you create this wave is by shaking and oscillating charges at particular frequencies. So if I wanted to send a different form of electromagnetic radiation, I could change the frequency. So now I'm shaking that charge even faster, and what you can see is that the wave changed shape. The distance between one peak and another peak got a lot shorter. Or what is the same for any electromagnetic radiation is how fast it travels. So it all travels at the speed of light, but changing the frequency, you can see here, changes the size and shape of our wave. So if you want a really wide wave, have a very low frequency. If you want a very short wave, then you have a very high frequency, which means wavelength and frequency are inverses of each other. And we know how to create these oscillating, changing magnetic fields. We talked about them with the LC circuits and the tanks. So in the one radio station, there's an LC tank circuit oscillating back and forth at a particular frequency. And what it does is it shakes the charges in the antenna at the frequency you want. Let's say it shakes it at 105.9 million hertz. I know how quickly those charges are going up and down in the antenna, and if I tune my radio to the same exact frequency, I can receive and have the charges in my antenna shake at the same rate. So the energy that is traveling along that wave moves at the speed of light and interacts with my antenna, creating the same frequency that the tank circuit. So I have a tank circuit sitting in my radio that is going to oscillate at the same frequency that comes from the station. And since the speed of light is a constant, like we said before, as the frequency of light increases, you can see the wavelength of light is decreasing. We're going from wavelengths in the radio waves that are in the kilometer range down to microwaves that are in the centimeter range. Even faster, we create infrared light. Right above infrared is a visible spot we call red light. That's the largest wavelength of light that we see. We see only this tiny sliver from 780 nanometers all the way to 400 nanometers, but that includes, that gives us all the different colors of the rainbow, Roy G. Biv. Beyond violet, if you start shaking that light even faster, we create ultraviolet light that is strong enough to damage living tissue. Even faster, higher frequency light, shorter wavelengths, we get X-rays, and even higher frequency light, we get gamma rays. So all that's changing for different forms of light is the wavelength and the frequency. The thing that stays constant every single time is the speed of light. So if you want to solve for a particular wavelength, or if a problem asks you what's going on, you know that the speed of light is always 3×10⁸, and you can solve for different wavelengths and frequencies based on what information you know. So if you're looking for the frequency of yellow light, you know the wavelength is around 600 nanometers, so you can put that in and give yourself a frequency times 10 to the 14th or 15th. But what else could light do for us? Well, light is energy. When energy comes towards us, we can actually use that energy to create forces. If you remember what pressure means, pressure, like in your tires, the pounds per square inch in your tires, that's a force per unit area. So if we look at that in terms of metric units, force is measured in newtons, area is in meters squared. So that means light actually creates a pressure when it interacts with different materials. The way we can calculate the light pressure here is the intensity of light divided by the speed of light. So what do I mean by the intensity of light? What I mean is, what are the watts of power delivered to every square meter? So remember, watts are joules per second. So if you would look at the intensity of the sun puts out a certain amount of wattage for every square meter on the surface of the earth. If I want to find the pressure that that light puts on an object, what I mean by pressure is the force that it pushes on it. Pressure, they say, is the intensity of light divided by the speed of light. So let's analyze the units to make sure we still get newtons per square meter. I already see the square meter in intensity, and speed of light is meters per second. Well, let's break down what a watt actually is. Remember that a watt is a joule per second. That's going to eliminate the second at least. And a joule is a newton times a meter. So that's going to knock out the meter here, and what's left behind in the end is a newton per square meter. So we do get the same pressure in light if we know the intensity of light and the speed of light. So when light comes in and hits a surface and strikes the surface, based on how intense that light is and how fast it's moving, it creates forces on that area. Now think back to momentum, when we had objects bouncing versus just hitting and stopping. Think about that now in terms of light. Light-colored objects versus dark objects. Objects appear white because they reflect everything that is striking them, and things that appear dark in color are absorbing all that light. So remembering the difference between a bounce and no bounce, to make something not bounce, all you have to do is stop it. In order to make something bounce, you've got to stop it and then throw it back. One of those creates a larger force and a larger impulse. So in the case of light and dark materials, objects that reflect lots of light feel twice the amount of force and pressure from light striking its surface than something that is dark in color. That object just absorbs the energy and the momentum of the light rather than reflect it. So based on the information I gave you here, you should be able to solve the few questions I ask you for Maxwell equations. The main thing that comes up on AP tests is a multiple choice question that asks about Maxwell. And really remember, Maxwell is the relationship between changing magnetic fields and changing electric fields. When one changes, it creates another one, and they travel at a particular speed. So this topic has opened up a whole new world that you can start exploring with what happens when these electromagnetic waves interact with other objects, whether they hit a reflective surface, a non-reflective surface, if they pass through materials like glass or water. But that's the whole topic of optics that you'll have to explore at another time.